A random variable is a variable that can equal different values according to some probability distribution or some random event. In the next chapter, we're going to talk about continuous random variables, but in this chapter, we're talking about discrete random variables. Usually, discrete random variable means it can only take on positive integer values. So here's a couple examples. The Dodgers are finishing the 2020 season playing 3 games against the Angels. When I originally recorded this video last week, the 3 games between the Dodgers and the Angels had not been played yet. So the Dodgers will either win 0 or 1 or 2 or 3 of those games. They can't win a negative number of games. They can't win more than 3 games since only 3 are played, and they can't win 1.7 games. So W, representing how many of those games the Dodgers win, W is a discrete random variable. It can only equal these possible values. And let's just say that the probabilities of those values are given by these decimal numbers here. Not really a big deal at this point where these decimal numbers are coming from, but what you do have to know is that all of these decimal numbers, all of these probabilities have to add up to 1. If these are the only possible values of the random variable, then the associated probabilities have to add up to 1. Also, those probabilities are often represented in a histogram. So we see bars for the possible values of the random variable, 0, 1, 2, and 3. And then the heights of the bars represent the probabilities. Here's another example that we're going to come back to several times in this lecture. Suppose you flip an unfair coin 3 times. And by unfair, we mean that the probability of heads is only 0.4, meaning that the probability of tails is 0.6. And let X represent the number of heads you observe in the 3 flips. So again, you could get 0 flip, you could get 0 heads, 1 head, 2 heads, or 3 heads. And here's the probabilities associated with each of those things occurring. So the random variable X will equal 3 about 6% of the time, but it will equal 1 about 43% of the time. And here's a histogram showing the distribution of those probabilities. And there's a variety of ways of writing this notation. I've seen professors get really hung up on the positive, the capital letters versus the lowercase letters. Technically, the uppercase letter X would be the random variable, and the lowercase letter X would be a particular value of that random variable. So sometimes you see lowercase p of X to mean the probability of a certain value of X, but that's also just the probability that our random variable X equals that certain value of X. My 2 examples here both happen to have 4 different outcomes for the discrete random variable, and many discrete random variables have a finite number of possible outcomes. And sometimes along with the probability mass function, we have a cumulative distribution function, or a cumulative density function. So always the first entry of the cumulative distribution is the same as the first value of the probability distribution. And then this probability here is 0.2 because it's the sum of these two, cumulative, accumulation. This is 0.5 because it's the sum of these 3 probabilities here. This is always, the last entry is always going to be 1 because it's the sum of all these probabilities here. And in example 2 with the coins, even though our probabilities are a little bit uglier, it's the same concept. This probability here is the sum of these 2. And this probability here is the sum of these 3, and so on. Note that you can find the probability of a particular value of X by subtracting the cumulative distribution function, which is indicated with a capital F usually. So you add up all the probabilities to 2, and then you subtract all of the probabilities added up to 1, as you see here. And when you do that subtraction, what you're left with is the probability that X is 2. You've got 0, 1, and 2, and then you're subtracting 0, 1, 1. So what you're left with is the probability of 2. Also, you can find a probability of a range of values of the variable by subtracting appropriately two values of the CDF. And I'm bringing that up because the book has a table that lists the CDF of certain random variables. So with a random variable, we sometimes want to talk about the mean, meaning sometimes the random variable x is a 3, and sometimes the random variable x is a 2. And we want to ask, on average, what does that variable equal? So you can imagine, for example, in the coin flipping example, flip the coin 3 times, write down the number of heads. Flip the coin 3 times again, write down the number of heads. Do that over and over again, and then find out on average, how many heads do you get? But it also makes sense to say, I'm about to flip the coin 3 times. How many heads do I expect to observe? So the term expect or expected value is kind of used synonymously with the term mean when we're dealing with random variables in general, but discrete random variables in particular. So this is not a mean the way we did a mean in chapter 1, because you can't just add these values of your variable together and divide by 4, because in this case the 3 is much more likely to occur than the 0 or the 1. So we have to do kind of a weighted mean, and by weighted, we're going to add up the values of the random variable, but we're going to add them up after being multiplied by the respective probabilities. So for example, in our example 1, our variable w could be a 0, 1, 2, or 3, and the probability of a 0 is 0.1, probability of a 1 is 0.1, probability of a 2 is 0.3, and so on. So each value of the random variable gets multiplied by the probability of that value of the random variable, and then those products get added together, and this is your expected value for the random variable, or your mean of the random variable. So in the context of this Dodger example, we expect the Dodgers to win 2.2 games. In other words, if they played this 3-game series with the Angels over and over and over again, if that was possible to do, on average, they would win 2.2 games. And with the coin flipping example, same thing. Each value of the random variable times the probability of that value. So a 1 times the probability of a 1, a 2 times the probability of a 2, and so on. You add up those products and you get 1.2, meaning on average, we expect to get 1.2 heads when we flip the coin 3 times. And don't feel the need to round that off. Just leave it as a decimal number. That's fine. I know it's not possible on any particular round of flipping the coin 3 times. It's not possible to observe 1.2 heads, but on average, we will observe 1.2 heads. And so pretty obviously, following our calculation of mean, there's also a formula for variance. And it's similar to a formula for variance we saw before, where you're taking the values of x and subtracting the mean and squaring those deviations. But then instead of dividing by n, we're going to multiply each of those squares by the probability of this value of x occurring, and then sum those products. And like we saw in an earlier chapter, there's another version of the variance formula where you can say the expected value of x squared minus the expected value of x squared. So you can sum the squares of the variables times their respective probabilities, and then after summing all those products together, subtract the mean squared. So let me show that both ways on both of our examples. So using example 1, where our mean was 2.2, you do each value of the random variable, which is 0, 1, 2, and 3. And for each value of the random variable, you subtract the mean, and then you square that difference. So for each value of the random variable, we're subtracting 2.2 and squaring that difference. And then each of those squares gets multiplied by the probability of the particular value of x. So in this case, we're doing 0 minus 2.2 squared, and then times the probability of a 0. Over here, we're doing 3 minus 2.2 squared, and then times the probability of a 3. You sum all those products together, and you get 0.96 for the variance of our random variable w. The alternate version of the formula over here, you can sum the values of our variable squared times the probability. So 0 squared, 1 squared, 2 squared, 3 squared, and each of those times their probabilities. 0 squared times the probability of a 0, 2 squared times the probability of a 2, and so on. And then after that summation is done, subtract the mean squared, and that gives you the same 0.96. So whichever way you calculate that 0.96, you can take the square root of that, and then you have the standard deviation. I should say at this point that this is also possible to do via the calculator if you don't want to do all those summations, but you just have to know a couple key buttons to press on the calculator. So if, for example, I have the values of my random variable 0, 1, 2, and 3 in one list, and then in the list right next to it, put the probabilities 0.1, 0.2, 0.1, 0.1, 0.3, and 0.5. And if we do second stat math menu sum, if we sum the product of those two lists, the values of the variable, I need 4 in here, I missed the 4. The values of my variable are in list 3 times their probabilities they're in list 4, and sum those products. That'll give me the mean also, 2.2. And I could also do second stat math sum, parentheses, the values of my variable in list 3 minus the mean, which is 2.2, square that difference, and then multiply by the probability that's in list 4. That's essentially our formula for variance, and that gives you the 0.96. There's yet another way to do this on the calculator. If you press stat calculate one variable statistics, you can tell the calculator to use the values that are in list 3, but use the probabilities that are in list 4. And when you calculate doing this, there's your mean of 2.2, and there's your standard deviation of 0.7978, which was the same standard deviation we got over here, 9798. 9798. And then if you want to square this standard deviation to get variance, you can go vars, statistics, sigma, and then square it, and there's our variance of 0.96. And since I used the variable that was already on the calculator, I didn't have to worry about any rounding off. So you can do it by hand for a small data set like this, or for a small random variable like this, and it's not that big a deal, but there's also shortcuts for doing it on the calculator. If we go through that with the second example, each value of x minus the mean squared times its probability. So remember, on the second example, our mean was 1.2. So I'm doing 0, 1, 2, and 3. Those are the values of my random variable. And each of those minus the mean of 1.2. And each of those differences squared. And then each of those differences times the probability of that particular value of the random variable. So 0 minus the mean squared times the probability of a 0. Plus 1 minus the mean squared times the probability of a 1, and so on. That whole calculation will come out to be 0.72. The alternate method is to do each value of the random variable squared times its probability, 1 squared times the probability of a 1, 2 squared times the probability of a 2, and so on. And after that summation is done, you just subtract the mean squared, and you'll get the same 0.72. I could also set this up on the calculator. I'll use two other lists on the calculator. I could put the values of my random variable 0, 1, 0, 1, 2, and 3 in list 5, and then their probabilities, which if I can remember, 216, 432, 288, and 064, put those in list 6, and then if I do stat, calculate one variable statistics using the values of my variable in list 5 and the probabilities of those values in list 6, this will tell me that the mean is 1.2 like we had before. There's our mean of 1.2, and the standard deviation is 0.8485, which we got down here. And then if I take the standard deviation squared, that'll give me my variance, which is 0.72. Since Connect Math gives us the option of sending our data to Excel, I wanted to show you how to also do these calculations on Excel. So if we go back to the first example with the Dodgers wins, if I put the possible values of the random variable in one column and I put their probabilities in the other column, then I can ask Excel to multiply those together, because that's exactly what we're going to do here in our formula. We're going to multiply together the values of X times their probabilities. So we'll say in Excel, multiply A1 times B1. That's a value of the random variable times its probability. And then if we copy that and paste, then we have all of those products. And then we can say the sum of those products, like that. Oops, I got an extra character in there. And we got 2.2, which is the same mean that we got right there. And in our other example, we had 0, 1, 2, and 3 with probabilities of 216, 432, 288, and 064. And once again, we can multiply those together and add up those products, and we'll get a mean of 1.2, which should be the same mean we got over here in the notes, doing it by hand, so to speak. There's a quicker way to do it that involves a different Excel spreadsheet function that comes in really handy in this case, which is sum product, which is exactly what we want to do. We want to sum a bunch of products. And what we want to take the product of is the numbers in A1 through A4, and we want the product of that with the numbers in B1 through B4, and sum those products, and you get 2.2 just with one spreadsheet function like that. Okay, and then for the variance, there's a couple different ways you can go. You can add another column. So this time do X squared, so A1 times A1 times the probability, which is in B1, and add those all up. So this is, if we go back to our variance formula, I'm summing the values of X squared times their probabilities. So if we investigate this formula, X squared, so I'm doing A1 times itself times the probability, which is in B1. And then I want to add those probabilities, or add those products together, and I get 5.8. And then I take that 5.8 and I subtract the number that we got for the mean squared, and there's our variance of 0.96. Same variance we got there. We can do the same thing over here. Create another column which takes the value of our random variable times itself, or in other words squared, and then times its associated probability. Copy and paste all of those products, and then sum all those products, and we get 216. And then let's take that value and subtract what we got for the mean, squared. And we get 0.72 for the variance, which is the same variance as we got that way. And then, of course, well, the way I usually do in Excel, the way I usually do square root is I'll just take this number to the power 1/2, and that'll give me the square root. It's 9797, which we had up here. And then over here, take that number there to the power 0.5. That'll give me square root 8485, which is the same 8485 we have there. One more thing, there's another shortcut in Excel for this 0.58. You can also do sum product again. This is for the variance. Well, not for the variance, but for the first piece of the variance formula, which is, let me scroll up, this piece of the variance formula right here, the sum of the x squareds times the probabilities, which is the 5.8 number here before I subtracted the 2.2 squared. I can do sum product, and since I want the values of x squared, let me make sure I can see all this. Sum product, since I want the values of x squared, I can just do the list A1 through A4 twice. So that's going to give me the product of A1 through A4 times A1 through A4, and then all of that multiplied times B1 through B4, and that's the same 5.8 number. So there's a couple different ways to get that done in Excel. There's my same 2.16 number. And remember, that's not the variance, though. The variance is you have to take that number and then subtract the mean squared. So I got from the 5.8 to here by, remember, by subtracting the mean squared. And then over here, I got from the 216 to the variance by taking the 216 and subtracting the mean squared. So that's how you do all that in it. So there's a variety of ways to get these calculations done. Now we turn our attention from random variables in general to particular, very special and important discrete random variables. Probably the most important of which is the binomial random variable. So our coin flipping example from earlier is a perfect example of a binomial random variable where you have a fixed number of trials. There's only 2 outcomes on each trial, which is sometimes referred to as a Bernoulli trial. And those 2 outcomes, for some reason, and this goes back like 300 years, but for some reason statisticians have always called those 2 outcomes success and failure. And the probability of success has to remain constant from trial to trial. And usually the notation for the probability of success is lowercase p, and the probability of failure is sometimes written as lowercase q and sometimes written as 1 minus p. We can write it as 1 minus p because there's only 2 things that can happen. So the probability of failure has to be the complement of the probability of success, so 1 minus p. And you have a random variable x that is counting the number of successes in the n trials. And when all of these conditions are met, then the random variable x is called a binomial random variable. So just to run through that with our coin flipping example, our coin flipping example had a fixed number of trials. We were flipping the coin 3 times. Each of those trials, each flip of the coin, had 2 outcomes, heads and tails. And I'm referring to heads as success because in that example, we were counting the number of heads. The probability of success remains constant from trial to trial. For every flip of the coin, the probability of success was 0.4, and we were counting the number of heads. So coin flipping is like, and counting heads or counting tails is like the quintessential example of binomial. But there's other such things, like you could select a random sample of voters, and every one of those voters is either going to vote on election day or they're not, or they're either going to vote for Trump or they're not. There's a lot of situations like that, Or you have a random sample of blood tests, let's say pregnancy tests, and each of those pregnancy tests is either positive or negative. There's a lot of different situations that fall into this two possible outcomes on a bunch of trials. So there's a formula for the probabilities of a binomial random variable. So when I gave these probabilities earlier, I didn't just make them up. They come from a formula. And so let's work through, it's going to be a little bit time consuming, but let's work through how you can figure out those probabilities, just knowing what we know from the chapter on probability. Just wanted to give you a warning. This next few minutes is going to be a little bit hard to follow, but at the end of it, there's going to be a formula and a really awesome shortcut on the calculator. The probability that x is 0, meaning you've got 0 heads. The only way you can get 0 heads is by flipping tails, tails, tails. And I'm going to write that as an AND probability statement. If you got tails, 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 that means the first flip was tails, and the second flip was tails, and the third flip was tails. Now, very important point that we were told that, the coin flips are independent. So since they're independent, we have a multiplication rule for independent events, and we can just write this as the product of these probabilities. The product of the probability that the first flip is tails times the probability the second flip is tails times the probability the third flip is tails. And remember, the probability of heads was 0.4, so the probability of tails is 0.6, and 0.6 to the third power is 0.216. Similarly, but a little bit more lengthy, for the probability that x is 1, that means you've gotten 1 head. That's a little bit tougher because there's 3 ways that can happen. The 2 tails here with 1 head, or the 2 tails here with 1 head, or the 2 tails here with 1 head. Now, since these events are disjoint, meaning if this one has happened, this one has not, since these events are disjoint, then you can write the OR statement as a sum of the individual probabilities. And then each of these probability statements we're going to write as a product like we did before. So the probability of tails, tails, heads, we're going to write as the probability of tails times the probability of tails times the probability of heads, and so on. And then we plug in the probability of heads and the probability of tails. And notice, even though they're in a different order, all of these statements are going to be a 0.6 and a 0.6 and a 0.4, because all of them had 2 tails and 1 head. So 0.6 times 0.6 times 0.4. So I'm going to first of all write that as 3 times 0.4 times 0.6 times 0.6, because we've got the same thing 3 times. And then I'm going to write the 0.6 squared instead of 0.6 times 0.6. And anyways, that product turns out to be 0.432. So that's where this probability came from. And then I'm going to work through something similar for 2 heads. And that comes out to be this probability. And with 2 heads, we have the probability of heads squared this time, and the probability of tails only occurring once. And then the probability of 3 heads is just the probability of heads times the probability of heads times the probability of heads, which is the probability of heads to the third power. And so then to try to motivate or show where the formula is going to come from, I'm rewriting the probabilities I had before as 0.6 to the third, 3 times 0.4 times 0.6 squared, 3 times 0.4 squared times 0.6, and 0.4 to the third, which was exactly what I was writing up here as I was going through those probabilities. And then just to make the patterns more obvious, I'm going to put a coefficient of 1 in front of here and in front of here. And even though this probability does not have a 0.4, I'm going to throw in a 0.4 to the 0 power. And 0.4 to the 0 power is 1, so that doesn't change anything. And I'm going to throw in down here a 0.6 to the 0 power. So now you can see this pattern of exponents. When you have 0 successes, you have the probability of success to the 0. When you have 1 success, you have the probability of success to the 1. 2 successes, the probability of success to the 2, and so on. And as the powers on the probability of success go up, the powers on the probability of failure go down. But notice that in every case, those exponents add up to 3 because there's 3 trials. And also notice that our coefficients 1, 3, 3, 1 are just coming from a row of Pascal's triangle, if you're familiar with Pascal's triangle. So this formula can then be written like this. The first number here is n choose x. So in this case, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. So those coefficients are just coming from our combinations formula. Then we have the probability of success to the x, 0.4 to the 0, 1, 2, 3. And then we have the probability of failure, which is 1 minus p, to the power n minus x. And some people get freaked out by this exponent, but this exponent is just a way of saying that if you've had 0 successes, you had to have 3 failures. And if you've had 1 success, then you had to have 2 failures because the total number of trials is n. So the number of failures is n minus whatever the number of successes was. So sometimes you see this formula with an x in it, and sometimes you see this formula with a k in place of the x, or maybe an r in place of the x. But that's kind of a common formula for binomial. So this can be done by hand, so to speak, on any scientific calculator. Let's just do one of these probabilities. 3 choose 1 times the probability of success to the 1 times the probability of failure to the 2. And there's 0.432 from our probability distribution table. So it can be done with any scientific calculator, but this graphing calculator actually has a binomial function built in so that I can do binomial PDF, tell it the number of trials, the probability of success, and the number of successes that I'm trying to find the probability of, and I'll get the exact same answer. So there's that from the calculator. And so it turns out there's also a table in the book that will give us these probabilities, and these probabilities are already calculated. There's a couple different ways to get to that table. If you're reading the ebook in this section on binomial, you will see a couple places where they have a link to table A. Right here, table A. Here's another one, table A. Here's a picture of table A. So if you click on that, that brings up this table, which begins with binomial probabilities. I also have the PDF on our web page. If you click on our website and click on tables, that'll bring up the PDF. A little bit easier for me to zoom on the PDF. And to use this table, there's binomial probabilities, there's our formula, and all you have to do is find the value of n, how many trials, and notice the number of trials keeps going up. There's n equals 10, n equals 11. This table is several pages long. So in our case, our n is 3. And then up here, you find the probability of success, which in our coin flipping example is 0.4. And you look at where this section for n equals 3 intersects with this probability of success of 0.4, and notice there's 216, 432, 288, and 064, exactly like we got off of the calculator. So the probabilities have already been calculated for us. The only catch is the probability of success has to be a nice probability of success. For example, if our probability of success had been 0.43, then the table's not going to help us. But if the probability of success is one of these numbers on the table and the value of n is one of the numbers on the table, then bam, you go right to the right section of the table and the probabilities have already been calculated for you. Also, if you remember our CDF from before. Let me scroll up a little bit. If you remember our CDF, the calculator also has a cumulative density function or a cumulative distribution function built in. So if you want to know all the probabilities up to and including 1, the sum of all those probabilities, that's second vars binomial CDF. And again, tell it the number of trials, tell it the probability of success, and tell it the number of successes you're interested in. But in this case, it's not going to tell me the probability of 1 success. It's going to tell me the probability of 1 success or less. So that's the sum of the 216 and the 432 from our PDF, and that's 648, which the calculator is giving us. So the calculator has the CDF built in, and there's also a table in the book. Okay, so let's do another example. We've already been talking about that coin flipping example a lot, but let's do another example. Nationwide, 30% of fifth graders can identify the state of Colorado on a map. Suppose we select 14 fifth graders at random and ask them to identify Colorado on a map. So we're going to assume that since these people were chosen at random, that they're independent trials. And we're also going to assume that all of them will have a 30% chance of correctly identifying Colorado on a map. So therefore we have our N, 14 independent trials, and they're independent, and the probability of success is 0.3 on every trial. So what's the probability that 5 of them can identify Colorado on a map? What's the probability that less than 5 of them can identify Colorado on a map? So our N is 14, our probability of success is 0.3. We want to know the probability of 5 successes. That's 14 choose 5. Probability of success to the 5th. Probability of failure to the 9th, because if you had 5 successes, you had to have 9 failures. So using the formula this way, you get 1963, or punching it into the calculator's binomial PDF function, you get the same 1963. Then what's the probability that less than 5 of them can identify Colorado on a map? So less than 5 means 4 and below. So 0, 1, 2, 3, and 4. We're going to find the probability of 0 successes, the probability of 1 success, and so on, and add those together. So we can use this binomial PDF function repeatedly on the calculator, or do this calculation repeatedly and get all of those probabilities and add them together. Or if you use the CDF on the calculator, 14 trials, probability of success is 0.3, and add up all the probability up to and including 4, and you get this same 0.584 number that we got right here. Okay, stay tuned for the next video. Next up will be the mean and the variance of a binomial random variable.